Question show time. Your questions, my answers. As always, wherever you are listening to this, watching this, anywhere, if a question pops in your brain on any video, just write it down. I'll gather them up and I will answer them here. And I've got a special guest answerer and I've got a special dog barking in the background, so I hope it's not too annoying. All right, let's get into the questions. Time logician. Could nuclear rockets or any modern rockets generate 1G of thrust for long-term periods? No, we don't have any rockets that could do 1G of thrust for long periods of time. Now, we have rockets that could do 1G of thrust for short periods of time. You could have like a chemical rocket give you 1G for a couple of minutes. Maybe a nuclear rocket would give you a few more minutes, depending on how much fuel you would have. But to go for long periods of time, for years, say, which is what you would want to be able to go to, say, other stars, or like the Expanse, where you fire your thruster for half of the journey, then turn around and decelerate, and you've got 1G of gravity the whole time. That would be awesome, and we have nothing like it. Not even like theoretically. Like maybe if you had like an antimatter drive, you could produce that kind of thrust for long periods of time, but in the near-term future, we will not have anything that can produce 1G of thrust. Here's the crazy thing, right? If you just produced 1G of thrust over the course of, say, a year, you'd be hitting relativistic speeds. You'd be closing in on the speed of light. And this is the weird part. Thanks to time dilation and relativity, you could accelerate at 1G for, say, 20 years. And you would get closer and closer and closer to the speed of light, and the distance to your destination would shrink so that you could travel billions of light years in your lifetime. And what objects are at the edge of the observable universe today, you could get to them in a human lifetime. We've done a whole video about that. I'll put it in the description down below because it's such a mind-bending idea. But no, there is nothing that we have in the near future that's going to be able to provide 1G of thrust for any long duration. So we're going to need some kind of artificial gravity system that we bring with us, something rotating that on the spaceship. So think Babylon 5. That's what we need. Phil Bugless. I have an unrelated question which you could possibly answer for me. Stars are born when the collapsing cloud has enough density that fusion kicks off and the star then blows away the rest of its cloud, yes? How are then stars of different size and mass created? Surely they would reach that density at about the same size. If a red dwarf completes its growth and starts fusing, how does a giant like Betelgeuse keep on growing for so much longer? I look forward to hearing your take on this. The size and mass of a star really just depends on how much raw material that it has to work with. So if you've got a big cloud of material and it starts to collapse, you're going to get a big star. If you've got a small cloud of material, then you're going to get a small star, or maybe a brown dwarf. And so really that's what defines it. Now there is a maximum size to the star that you can have. If you've got a star that's so big, say 60, 70 times the mass of the sun, maybe 100 times the mass of the sun, the star is so massive that as it starts to accrete that material, those really powerful stellar winds kick in and it actually blows away any additional material that's trying to infall in. So really the size of the star depends on how much material you've got to work with, up into, say, 100 times the mass of the sun, and then beyond that, yeah, you get to this point where material is starting to trying to fall in, the winds are blowing out because the star is so powerful, and no more material can fall in, and that limits the maximum size of what a star can be. But for the smaller ones, no, it's just how much material you've got to work with. David Curie. What do we know about the relative contribution of heavy elements from supernovae versus neutron-neutron star mergers? If you asked this question 5 years ago, the answer would be that the heavy elements beyond iron came from supernovae. And the thinking was, right, that inside a gigantic star, it's fusing in its core, say hydrogen into helium, and then it runs out of hydrogen in its core, and then it switches to fusing helium together, and then it runs out of helium in its core, and it switches to fusing oxygen together, and you get these shells forming inside the star. And over time, the star works its way all the way up to the point that it's actually trying to fuse iron in the core. And the problem is that once you have iron, you don't get any additional energy out of fusing iron the way you do with all of the other elements. So at that moment, the fusion inside the star ceases and all of the outer layers collapse in on itself. You get a black hole or a neutron star, and then you get the explosion of the supernova, and all this material is thrown out into space. This was sort of the traditional idea of how we got the heavier elements. And so when you think about the gold in your ring or things like that, that it's this mind-bending idea that this was when a star died. But in 2017, we saw the kilonova, where thanks to both gravitational wave and visual astronomy, we saw two neutron stars spiral into each other and collide. And then they detonated as a type of gamma ray burst and released a tremendous amount of energy, but as well the actual gravitational waves of them spiraling in were also detectable at the same time. Now this told us that light and gravitational waves move at the speed of light, but the really amazing thing was that astronomers saw this huge cloud of gold and other heavier elements in the region where these two neutron stars collided. And this was theorized. Astronomers had thought, okay, maybe in addition to the way supernovae deliver, heavy metals into the universe, maybe colliding neutron stars do it as well. But that was just a theory. And now here we are, 2 years later. We know for certain that neutron stars collide. We know for certain that they release these heavier elements. And now the question really is, and this is still a bit of a mystery, what is the percentage? Is it that we're mostly our heavy metals are provided by neutron star collisions? Is there a mixture, some from neutron stars and some from supernovae? And actually, the research is still ongoing, but it's starting to push towards the idea that it's neutron stars colliding with each other and not supernova, which kind of makes sense because, when a supernova goes off and it implodes on itself, it takes a lot of that heavy material with it into the black hole. It's surprising that any of it actually makes out. So here we are, you're watching the evidence build and the science change over time. And I'm sure in a couple of years, I'll be able to give you a much more concrete answer as we go on. It's amazing though, I really like it. James T, just for fun, what would the canceled overwhelmingly large telescope be capable of, which the E-ELT will not be able to do? All right, so just to give people some context here, the overwhelmingly large telescope was the telescope that the European Southern Observatory was originally planning to build. It was going to have an aperture of 100 meters. And because the price was going to be too expensive, say a couple of $1 billion, when you think about the price of the James Webb telescope closing in at $10 billion. Anyway, they decided not to build that, and instead they're going to build the extremely large telescope. And the extremely large telescope has an aperture of 39 meters. So the overwhelmingly large telescope was going to have a diameter of roughly 2.5. Now what is the resolving power? It's going to have 2.5 additional times observing capability over the extremely large telescope. And it would allow it to take things to the next level, kind of jump a generation of telescopes, while the extremely large telescope is going to be able to view planets orbiting other stars from the surface of the ground here on Earth. The overwhelmingly large telescope would have been able to take that to the next level and be able to observe smaller planets closer into their stars, to be able to do more precise radial velocity method measurements, be able to see fainter objects farther out into the universe, gather light more quickly on an object so that it would be able to reduce the amount of observing time that astronomers would need. It's just more bigger, and it's the kind of telescope that I really wish they built. And I hope that they do come back and take another crack at it, because it seems like a bargain compared to some of these space telescopes for the size and capability. And the thinking is that at 100 meters, you've reached really the maximum size that a telescope can be. You can't go any bigger than the 100 meters on Earth. Any bigger than that, and you're going to have to go off into space. But can you imagine putting the overwhelmingly large telescope in space? Now, that would be amazing. Jonathan Adami. Question about time. It said that the farther away you get from our gravity well, the slower time passes relative to people on the surface. Hope I'm getting this right, but I've read something about GPS satellites that have to account for it already. If we assume that we have people living on the moon and Mars, how would we all age relative to each other? Would there be any significant difference? Like, if I take a trip to Mars and come back in 10 Earth years, is it 10 years later on Earth? So you're describing this idea of time dilation, and there's like two factors that will push into time dilation. The first one is, what is your sort of, how close are you to a mass? So if you're standing on the Earth, you're experiencing time dilation compared to somebody who is far away. And of course, think about the movie Interstellar. Think about how they went down to this world that was orbiting around a supermassive black hole, and they were there for like a couple of hours, and when they came back out, decades had passed for the rest of the universe. So it's that same idea. But instead of it being you being here on Earth for hours and people out in space living for decades, it's more like you experience a few less nanoseconds than they do. It's very subtle. The other thing that contributes to time dilation is speed, about you moving. So in other words, a person who's orbiting around the Earth going 27,000 kilometers per hour is experiencing time dilation in the other way. So they're experiencing less time than you are here on Earth. And there's, of course, this perfect point where they actually balance out, where a person can be orbiting the Earth at the same speed, so they experience the exact same amount of time because the two time dilations cancel out. Now, you're talking about a person going to Mars. And so let's think about this, right? You're standing here on Earth, you're experiencing a little bit of time dilation because you're in a greater mass than a person who is standing on Mars. But the amount of mass is not that much, right? The difference, the time dilation, it's going to be nanoseconds. And then the other contributor is the velocity. Now, here on Earth, we're moving at 30 kilometers per second around the sun, while people on Mars are actually moving more slowly as Mars goes around the sun because it's farther away from the gravity well. But as you approach Mars, the time dilation is going to be one amount, and then as you pass Mars and it's sort of moving in a different direction compared to you, the time dilation numbers will change. So really, the amount of time dilation that you're going to be experiencing will just change over the course of the entire orbit. Sometimes you're moving in a similar speed to the people on Mars. Other times you're moving in a much greater velocity compared to Mars. But just being far away, being at Mars, traveling to Mars and then traveling back, those will contribute as well. But the distance, and I think that's what you're thinking about, is like, if a person flies out to Mars and now they're far away, will they experience a lot of different time? And the answer is not really. And again, all of these numbers, you could add them up to be nanoseconds. Like, you would require the most precise atomic clocks ever made to be able to tell any difference between the amount of time that you've experienced here on Earth and, say, the amount of time that people who've gone to Mars and come home have experienced. It's really tiny. Max Q. Hey Fraser, do the moons of Uranus orbit around the equator of the planet, or do they orbit in the plane of the ecliptic? Great question. Uranus, of course, is one of the weirdest planets in the solar system. While, say, Earth is turning with a tilt of 23.5 degrees, Mars has about the same kind of axial tilt. Uranus has been knocked completely over on its side. It's almost like it's just rolling sideways. So the question then is, are the moons doing the same thing, or are the moons tilted over and orbiting sideways with Uranus? And the answer is, they're orbiting with Uranus. So astronomers have tried to figure out what could be the kind of event that would cause something like a gigantic planet like Uranus to roll over onto its side. And one idea is just some gigantic collision back early on in its history, and that's been proposed. And then the other idea is that early on in the solar system, there's a lot of gas and dust left over. And as the planets were moving through this gas and dust, they were accumulating additional material and actually was causing a torque in their orbit. And so Jupiter, Saturn moved out into the solar system, and Uranus and Neptune actually flipped locations. So originally, it should have gone Jupiter, Saturn, Neptune, Uranus, but through that planetary migration, they switched places. And maybe in that switching places, that caused enough of a torque on Uranus to flip it over onto its side. Still a fascinating place, and we definitely need to go back. So if you've got any plans to send missions, I suggest Uranus. It's we need to go back. Gas dive. why don't we send up a large telescope in parts and get the astronauts on the ISS to assemble it? I see NASA has got as far as having a report on the feasibility of launching an investigation into the prospect of writing a report about this idea, but no farther. Seems like a complete no-brainer. The James Webb Space Telescope is hard because it has to self-assemble, so don't make it self-assemble, get people to do it. You're absolutely right. This idea of launching some kind of telescope to the International Space Station and attaching it and having the astronauts assemble it and they can maintain it, like it makes a certain amount of sense. But James Webb is going to be launched in one telescope. It's going to be sent out to the L2 Lagrange point. It's going to have to unfurl itself and unfold like a piece of origami. Seems kind of dangerous, right? Why are they doing that? Well, the big reason that they're doing that with James Webb is that they need to get James Webb to a place where it's not going to require much fuel to maintain its position, and it needs to be able to keep itself very cool. And the way it's going to do that is it's going to unfurl this great big sunshade that's going to protect itself from the sun. If James Webb was orbiting the Earth, it would be coming into and out of the sunlight. It would be getting warm and cold and warm and cold, and that would mess up the optics. It needs to be incredibly cold so that it can observe the universe in this really faint infrared. You could imagine some future maybe where we have a gigantic space station at the L2 Lagrange point, and then yeah, maybe you do assemble a really great infrared telescope out there. But even that, maybe it's going to be too close to the station, and so the radiation, the heat that's coming off the station will mess with the sensitive infrared telescope. Like with an infrared telescope, it's got to be incredibly, incredibly cold, just a couple of degrees above absolute zero. And we have anything that we do is going to be giving off heat, and it's going to mess with the telescope. Now, with the LUVOIR telescope, it doesn't have to be so sensitive. This is this next generation telescope, large ultraviolet infrared optical telescope, but it's going to be near infrared, not far infrared, like Hubble Space Telescope. And one of the ideas is that it will be attached to the Deep Space Gateway, that parts of it will be sent up, astronauts will assemble it, and they'll be able to maintain it and be able to swap out the instruments, and that'll be one of the reasons for the Deep Space Gateway. So James Webb doesn't make sense, but with a telescope like LUVOIR, more of these general purpose big telescopes, it does kind of make sense to attach them to the International Space Station. And in fact, one of the ideas back with the Apollo missions back 50 years ago, after they wrapped up Apollo 17, Apollo 18, they were going to continue, and one of the things that they were thinking of building was a telescope on the moon. The astronauts would assemble a telescope on the moon, and then maybe that would serve as the beginning of some constantly inhabited lunar station. But of course, they didn't go back, they didn't continue after a certain point, and that telescope never got built. But in general, planets, moons, they're not great places to build telescopes. Space is sort of the best place to build a telescope, and you don't want it to be close even to a station with its electronics, with the heat that the station is giving off. So I think we will, in the future, we'll find out. These tests will happen, and we'll see what's going to happen with if LUVOIR gets attached to the Deep Space Gateway. Cheesy McGeezy. Not a question, but a confession. The sun scares me. I'm afraid we're going to fall into it somehow, even though we've been orbiting it for billions of years. I'm afraid it's going to die much, much sooner than scientists predict. I'm afraid of the form of the death being a supernova, despite astrophysicists informing us that it will expand into a red giant. I'm afraid of coronal mass ejection, solar flares. I'm also afraid of other stars and black holes coming too close, especially black holes that we can't even see coming. Even though I know if this were all going to happen, it would happen over the course of millions of years, long after I'm dead. And I know we have solid models and solid math that all fit together like a puzzle, and it would be very surprising for scientists to be oh so wrong about this, but it's still something I worry about all the time. That's sad. Don't worry about the sun. Don't worry about any of this stuff. So let me see if I can put your mind at ease in a couple of places. So the first thing is that the sun is the hardest place to get to in the entire solar system. Right? Think about us. We are orbiting around the sun at 30 kilometers per second, and the only way for us to fall into the sun would be to cancel out that orbital velocity. And if you're going to go from, say, the surface of the Earth into Earth orbit, it's 8,500 meters per second, 8.5 kilometers per second. So that is a fraction of the speed. That's like going into orbit. And if you want to go to the Mars, you just got to add a couple more kilometers per second. But to go to 30 kilometers per second, that's really hard. So the sun, like no matter what you try to do, you cannot get into the sun. It's just like so hard. So you're not going to fall into the sun. The sun is not going to form a supernova. And again, as you said, we have models. We understand. We look out and we see the different kinds of stars that are like our sun at every single stage of their evolution. And we understand very well what the future holds for our sun, that it's going to take another 5 billion years before it runs out of fuel in its core and turns into a red giant and burns out the planets in the solar system. So that's not going to happen. Now, the sun and the planets have been orbiting around the sun almost perfectly, right, for 4.5 billion years. So even though we have probably had close passes with other stars, with dwarf planets, with black holes at some point, none of them have been close enough to really affect our solar system in any way, shape, or form. And that's in 4.5 billion years. So, like, I know these things are enormous, and the sun seems like this really, it's a ball of fusion, an ongoing thermonuclear reaction, and it's right there. It's the source of life on Earth. It's the reason we get a chance to do any of this stuff. So don't worry about the sun. Don't worry about these existential things. It's about putting on your car seatbelt. It's about getting enough exercise. It's about eating healthy foods. These are the kinds of things that we really, truly need to be worried about. So don't worry about that. You've got hundreds of millions, if not billions of years before something cosmologically happens to the planet. Jonathan Hobbs. If two neutron stars collided, would they always make a black hole? If they didn't make a black hole, is it 100% of the mass from the two bodies that collided be captured in the remaining body, or does some escape from the sheer energy during the collision and gets blasted out into space? I'm a huge fan of the show, and I'd really like to know what you think. So we talked earlier about this idea of the kilonova, that at one point, two neutron stars can whirl around each other and collide, and they detonate. And what remains? We know that tons of gold and other material was seeded out into the universe, so definitely something gets out. And astronomers are still trying to figure this out. Again, this is all relatively new. We've only seen one, maybe a second kilonova. And what appears to happen is they either collide and form a new neutron star. Enough material gets blown out, they come together, your remnant is another neutron star, or maybe the two collide, you add up their mass, and now you get a black hole. And this is something that astronomers are still trying to work out. And the only way they're going to be able to do that is to see more examples. Right now, we've only got the big one. We want more examples of kilonovas so that we can study them more carefully and start to piece together what happens. What is the object that remains when these two neutron stars smash into each other? Neutron star or black hole? Stay tuned. Aero Astro Arts. Love the show. Sorry to hear about the threats. But at 1756, you said oxygen, metal. If I remember the periodic table correctly, oxygen is a non-metal. Do astronomers, planetary scientists have different classifications than the periodic table? Keep up the great content. You're referencing the death threats that I get. Yeah, so astronomers are funny. Now, obviously, astronomers know the periodic table of elements, but in the minds of astronomers, there is the hydrogen and helium and a little bit of lithium that was formed during the Big Bang. And then there are all the other elements in the universe that were formed through other processes. So, at the hearts of giant stars, doing nucleosynthesis, or during the death of a giant star, when two neutron stars collide with each other and blast out all this material, these form the heavier elements. And astronomers call these metal. So anything that is heavier than lithium, hydrogen, helium, lithium, everything else, they refer to as metal. And Obviously, they know that it's not, they're not metal in the way that iron is metal, or that gold is metal, or that nickel is metal, but just that they are more than the original elements that formed the universe. You'll see this, and it's important for you to understand this, because you will see astronomers describe a star as saying having low metallicity or high metallicity, a high metal star or a low metal star. And when they're talking about a low metal star, they're just talking about something that has hydrogen, helium left over from the Big Bang, but not much else, not much other elements sort of mixed in that came from some other source. While a high metal star is going to be one that's going to have the hydrogen, the helium, but it's also going to have smatterings of oxygen and silicon and iron and other stuff in it that was formed through other stars, through supernovas, through nucleosynthesis, things like that. And it's thought that you need the high metal stars. Those are the ones that will produce places that can have planets and things like that. And so often if you see a low metal star, you're not going to expect to see any planets. A high metal star is the kind of place that you might expect to see planets. So astronomers just have a different definition for it. Razor Blate 79. Is dark matter constricted to the outside of galaxies, or can it be found in between star systems? And does it float in the entire intergalactic medium, or does it stick to the edges of galaxies only? Great question, and I'm going to call in a ringer. I'm going to call in a specialist. This is Sophia Gad-Nasr, who is a astroparticle physicist studying dark matter at UC Irvine, and she's got an answer for you.
Is dark matter evenly distributed throughout the universe? Now, this is a really interesting and important question, because it is the fact that dark matter is not evenly distributed throughout the universe that we see galaxies today. So we know dark matter doesn't interact with light because we can't see it, but it does interact with gravity. And it is, in fact, its interactions with gravity that allow us to detect it in structures like galaxies and galaxy clusters. Now, the fact that it interacts with gravity means that it will also clump up towards itself under the effects of gravity. And it did this in the early universe, forming these clumps and sort of filaments that we call this dark matter cosmic web of dark matter. And it is towards these clump and dense regions of dark matter that regular matter kind of went and gravitated towards and condensed to form stars and galaxies that we see today. So throughout the universe, dark matter is not evenly distributed. Now let's look at what its distribution looks like in something that's a little bit more familiar to us, like our cosmic home, the Milky Way. The Milky Way is a spiral disk galaxy, and in spiral disk galaxies you have stars orbiting the central region on this sort of plane, a disk plane. This is where you have your spiral arms. They orbit around this sort of disk plane, around this central giant bulge region that has a whole bunch of like really old stars in the center surrounding this supermassive black hole right in there. So you have this bulge and then, a disk of stars orbiting right around it. And the way that dark matter sits in these galaxies is that it surrounds all of it in this giant spherical thing, engulfing the whole disk galaxy in this thing we call a halo. So dark matter kind of sits there in this giant spherical structure called a halo, engulfing the entire disk galaxy, which sits here in this, the disk part is here, and then you have your bulge in the center. And of course, in the bulge region, you have a lot more stuff, you have a lot more matter in there, which means that you'll have a higher gravitational potential. And because dark matter interacts with gravity, then you'll also have a higher density of dark matter in the central regions of the galaxy. So that moving, in the center, you'll have the highest density of dark matter, and then moving outward, the density decreases as you go outward and outward. So then in the disk of the galaxy, you will also have a lower density of dark matter. So you don't have all that much, but you have some still there. So there is dark matter there. Then that kind of raises the question that, well, since the solar system happens to be in this disk region, why don't we see the effects of dark matter in the solar system? Well, if you were to take all the dark matter and all the dark matter in the solar system, sum it up, and take its mass contribution and compare it to the mass of the sun, in this really small region of the galaxy, the solar system doesn't take all that much space, right? So in this really small region of the galaxy, the mass of the dark matter in there compared to the mass of the sun is negligible, which is why we can't see the effects of dark matter in our solar system. But there is dark matter here. In fact, it's everywhere in this room right now too. I actually made this calculation, and in many models, in many dark matter models, we kind of take this assumption and assume that the dark matter particle mass is of order 1 giga-electron volt, which is just a little bit higher than the mass of the proton. And if you were to do that, then if at any given moment, about 20,000 dark matter particles are passing through you, through me, and through everyone, and we don't feel a single one. That's how weird dark matter is. So to sum it up, basically dark matter is not evenly distributed throughout the universe, but if you want to find dark matter, you kind of look for the stars. Generally, where you see regular matter in stars is generally where dark matter is going to be. So to track dark matter, you look for the regular matter. Stars is where the dark matter is going to be, in general.
Thanks, Sophia. That was awesome. Again, I love having astrophysicists that I can reach out to help me with some of the answers to these questions. Anyway, that was a lot of fun. Thanks for everyone who sent in your questions. As always, wherever you are on my channel, if a question pops into your brain, write it down. I'll gather them up and I'll answer them here. All right, I'll see you next week. Thanks, dog. That was fun. You really helped.